Let's talk about the pseudocode for a graph breadth first search function. So we talked about these data structures of a frontier and a visited list. We've also talked about how we can potentially add additional logic on top of this vanilla breadth first search function. Let's take a look at the version where we need to generate these paths from one node to another and look at the pseudocode for doing that. So we have talked about how with our frontier, we want to keep looping while this thing is not empty, right? So to start, we need this idea of a frontier, and I'm going to use a queue data structure to represent this. We know we need this to be a first in, first out. And we also need something that's going to contain our list of nodes that we've already visited, right? So this could be a vector or a linked list or an array or whatever you want it to be, as long as you can add more nodes into it in some way. And so here's this container called visited. So to start, we want to add our beginning node, our start node, into both our frontier and to our visited. So we need to do something like this. Frontier dot push or put or add whatever the functionality is, add the start node that we want to start our search from. Same thing with our visited. Our visited, we want to add or push or whatever it is, our start node as well, right? So add our start node to both our frontier and visited. And now we want to keep track of, or we want to keep looping, while the frontier is not empty. And while the frontier is not empty, we need to do a couple things. The first is we need a node that we are currently exploring. I'm just going to call that current. And we need this to be equal to the next node from the frontier. Now I'm going to call pop, right? You can imagine that this could be a push or a pop. This could be a pop or a remove or like a DQ or whatever you want to call this function. But the point of this line here is the current node that we are exploring needs to be the next node from our frontier, which is a first in, first out data structure. And it also needs to remove that element from the frontier, right? The next thing, we need to loop through each of the neighbors, right? Or each of the connections of this current node. So for each connection inside of current's connections, right? So I'll just call this for each connection in current dot connections, right? But the idea here is that we're looping through each of the adjacent nodes, each of the connected nodes to the current node that we're exploring, right? And then we say, if that node is not in the visited list, if the connection is not in the visited list, then we want to add the connection to both our frontier and to our visited list. So add the connection to the frontier, as this is a node we need to explore in the future. Add the node to the visited list, as this is something we have already added, right? So we don't need to add it again. And this is it. This is the entire pseudocode for a regular plain breadth first search. Now, how do we augment this to be able to provide us the path in which one node is connected to another? Well, to do that, remember back up here in our diagram, we need to keep track of every time we add a node into our visited, we need to keep track of which node it was that added it. So we need to keep track of something else, right? In this case, we could keep track of, and I'll do this again in blue. In this case, we could keep track of some sort of like dictionary or a map or something else that essentially tells us from this node, here's the node that we came from, right? So In this case, we can assume that this is a dictionary or a map, and we can call this thing, so I'm going to call it a map, and we are going to call this came from. And to start this whole thing, we also need to make sure that here we say that that start node, that the start came from nothing, right? The start node came from nothing, right? It's our start node, right? So we can add this in there as having like a null value. This node came from nothing, came from a null value, right? The next thing we can do is we can say, well, down here, when we add something into our frontier and we add something into our visited list, we also can add it into our came from dictionary or came from map. And we'd do something like this. We'd say came from this connection came from the current node that we were exploring. Right? That's it. Just adds one more data structure. It looks like this, either a map or dictionary, depending on what programming language you're in. We say that the start node came from nothing. And then whenever we are adding a new node to the visit list, we say, well, this node is being added because it's connected to the current node we are exploring, right? And now, finally, this doesn't actually create the path for us. What this does is it just creates this data for us here. I came from H. H came from G. G came from A, right? So the last thing that we would need to do is we would need to write one final loop that essentially says from the goal node, right, from this node I, or from our end result node that we're looking to go to, from that, we can loop backwards through this dictionary to figure out how we got here, right? So in this case, if we were to go back and look at this diagram, our came from dictionary, let me just move this aside real quick. Our came from dictionary would end up looking something like this. I came from H. H came from G. G came from A. F came from E. E came from A. D came from A. C came from B. B came from A. This data that I've just written out here in my came from dictionary is literally just the data that I'm representing here with arrows, right? It's the exact same data. This is in a data structure. This is just represented visually in this nice diagram that I drew. And now based on this data, we can say, well, how do we get from A to I? Well, we can ask ourselves the question of how did we get to I from A? I came from H, and then H came from G, and then G came from A. There's our path right there. Our path is I to H to G to A. Now you may notice that's in reverse order. So if we go backwards like that, the last thing we need to do is reverse that list, right? Or we add the nodes at the beginning of whatever, list of nodes we're traversing through. So we end up with this list saying to go from A to I, we go A to G to H to I. This here is the final pseudocode that you need for the entire algorithm to do a breadth first search when you are trying to explore from one position to another and figure out how to get there. As a last and final note, the came from dictionary, in this case, there's one small optimization we can make. The came from dictionary is storing every single connection. So notice how whenever we add something to visited, we also add it to came from, right? Because of this, you can actually remove the visited list completely. So to tweak this and to optimize it slightly, we could theoretically remove the visited list, just like this, right? Remove the visited list here, and then in favor of saying if the connection is not in visited, we can say if the connection is not in the came from dictionary, right? Because any node that would be in our visited list would also be in our came from dictionary. Just a small optimization to save you one data structure there.